Thus, we asked the question, can we disrupt unsupervised learning by disrupting LTP? It is known from previous studies that inhibition of NMDA receptors blocks hippocampal LTP, as well as hippocampus-dependent memory in tasks such as water maze. CPP is a commonly used NMDA receptor antagonist that blocks NMDA receptors. And thus we tested with the CPP treatment on measures of learning in an unsupervised learning paradigm. We used a 2-day paradigm this time and measured the response of 2 groups, experimental, treated with saline, and CPP trans, as treated with 10 milligram per kilogram CPP, which has been shown to block spatial learning in the past. On day 1, animals are introduced in the complex environment with the objects in the dark compartment, and day 2 remains the same as day 1. What we find that both groups of animals start out exploring their environment with high percentage of movements, which decrease over time as they become familiar with it. However, looking at the changes on day 2, we see that exploratory animals not treated with CPP show experience-dependent changes from day 1 to day 2 as they decrease the number of movements, the duration of movements, and the time that they explore the familiar object. Looking at the CPP-treated animals, we don't see this day-to-day change, and the rats act on day 2 just the same as we're acting on day 1, suggesting that they did not gain experience on day 1 of exploration, similar to the way patient HM would react to the environment that he explored on the previous day. In conclusions, the analysis of the young male rats showed that we set up a behavioral paradigm which allowed us to measure different types of learning simultaneously, from locomotion to habit forming to object recognition. We've shown that 60 minutes of exploration is sufficient for rats to form long-term memories in the environment, and that the measures that block LTP also block learning in this test. So the next question we want to find out, if we tested animals that have LTP deficits in this test, would they show deficits in measures of learning that we've set up? So the first model of LTP deficit that we pick is a rat model for menopause. It's known that menopause is associated with changes in cognitive function, memory, and increased anxiety. Overactimized rats mimic this postmenopausal condition of memory impairments in rats, and memory impairments as well as anxiety. And it's been previously found that LTP is deficient in these rats, and importantly that estrogen treatment facilitates these LTP deficits. The experimental paradigm that we used was middle-aged 8-month female rats. One group was treated with vehicle, another was treated with estrogen for 2 weeks. And these animals were exposed to the 4-day learning paradigm that I previously described. The same measures of learning were also measured: percent time moving, number, duration of moves, distribution of activity, and the time spent with the object. What we find is overactimized rats treated with estrogen have similar activity levels to young rats. They start with high activity levels, which gradually decrease over time. This is related to a slight shift into the dark compartment, but not great enough to decrease the movements along the way. Looking at the non-treated OVX animals, we can see that their behavior decreases significantly by 30 minutes on day 2. This reflects their shift in distribution of the time into the dark compartment quickly. Looking at the day 3 traces, we don't see any experience-dependent changes from day 2 to day 3, suggesting that these animals are fundamentally different from young adult male rats in the way they respond to experience of the environment. To further characterize if any kind of experience-dependent learning has taken place, we look at the distribution of the animal's time over the exploration period. What we find is estrogen-treated animals have shifted their behavior from day 2 to day 3 to spend more time in the open field and away from the refuge. This was significantly different from one non-treated, which distributed their time equally from day 2 to day 3 and did not show experience-dependent changes from day 2 to day 3. Thus, this data shows that estrogen treatment allows the animals to have these experience-dependent changes.
Do you believe that's anxiety?
Yes. we actually did some literature search, and these animals do have signs of anxiety, and that's what this data is suggestive of. That these guys spend much more time in a dark compartment. Specifically, they go there much sooner. So this perhaps does show a sign of anxiety that these rats know to have.
What are the normal females look like?
We haven't characterized normal females, and it's really hard to characterize normal female behavior in these kind of tests because of the 4-day estrus cycles that they go through. So having them go through a 4-day testing period could produce dramatic changes that might be related to the hormone levels. And as we see, hormone levels have huge effect on behavior in the female rats. Thus, it's really difficult to characterize them. And usually, the OVX treated with estrogen serve as the control for this dysfunction.
Okay. So it's hard to know really what overactivity really does.
Exactly, yeah. Right. And also, estrogen does have side effects, so it's not really mimicking what normal females would do. But you're right, it doesn't really. It would be really hard to test normal female behavior.
Right. Well, yeah, put everybody on a pill or something.
Right.
I think another way to flatten the estrus. I withdraw that.
So then we wanted to further understand if this exploration on day 2 and day 3 in estrogen-treated and non-estrogen-treated animals resulted in their familiarity with the environment. So we introduced a novel object on day 4 and measured the animal's response to a novel object. What we see is estrogen-treated rats responded to novelty by significantly increasing their contact time with the object as compared to familiar object. However, the non-treated rats did not respond to the novelty and spent the same amount of time as they did with the old object and the familiar object. Also, setting the medium criteria for novelty detection, we find that 80% of the estrogen-treated rats responded to novelty, while only 20% met this criteria for novelty. All right, so we found that these rats have significant memory problems, and the estrogen can facilitate and improve these problems. Next, we wanted to look at a mouse model of early-stage Huntington's disease, because it's known that these mouse models are accompanied by cognitive decline, which progressively worsens, and these mice exhibit LTP impairments as well as learning impairments. We used a knock-in mouse of the disease because it provides a window of opportunity of studying this cognitive decline before the onset of the motor symptoms. Usually the characterization of the Huntington's mice involves a battery of behavioral tests to separate the locomotor deficiency versus cognitive deficiency. So we wanted to see if unsupervised learning paradigm can separate these two components and study them in one test. So this is the experimental paradigm. We had 4-month-old K40 knock-in mice, which I previously been shown to be in the stage before the striatal degeneration, but have cognitive impairments and were and age-range controls. The animals were exposed to the 4-day learning paradigm, as I described, and the same learning measures. So what we find by looking at the animal activity over time is they start out with high activity levels, which decreases only very slightly throughout the 60-minute testing period. On day 3, we do not see any change in experience-dependent behavior, and mice remain very active in this behavioral test, which also does not involve a shift in the dark compartment. They spend a large amount of time exploring. Looking at the distribution of time in the wild-type mice, we see the wild-type mice show the experience-dependent change from day 2 to day 3, but also shifting their time in the open field from the dark compartment. Looking at activity levels of K140 mice, we see that their activity levels are about 20% less than that of wild-type mice, suggesting the beginning stages of striatal degeneration and movement impairments. They also do not show day 2 to day 3 changes in behavior, and they do not show changes in the distribution of the behavior over time. To further characterize the memory and the memory problems in these mice, we looked at how they respond to novelty. So we introduced a novel object. And what we find is the wild-type mice respond to novelty really well by significantly increasing their time. The KAG140 mice also seem to respond to novelty, but not to the same degree. So we wanted to find out what percentage of these mice are the detectors that notice the novelty. We find that wild-type mice, 72% of the wild-type mice notice the novelty, while only 24% of the Huntington mice met the criteria for detection, suggesting the heterogeneity of memory problems in these mice. Few of the mice were able to have the memory, while the majority of the mice had memory problems. The concluding study from dysfunctional models show that overoptimized non-treated rats have no change in spatial distribution reflecting anxiety of the open field. They have a problem with object recognition, which was facilitated by estrogen treatment. And Huntington mice have decreased percentile moving, which might reflect a motor deficit, deficient over-day distribution of behavior, as well as deficient novel object recognition. We're able to characterize the dysfunction in both rodent, rat, and mouse models of the human memory disorders and show differences between different species, how they respond to their complex environments.